Okay, we are going on with the next talk by Chris Ure on the tautological classes of Matroid. Thank you, Chris.
Yeah, thank you. So today I'll tell you these three things. I'll first tell you a tale of two rings, very well famous studied rings, so-called K-ring and the H-ring or the cohomology ring. Then I'll tell you how these things called matroids fit into the picture. And then finally I'll tell you how our work makes it such that really there's one ring to rule them all. So let's get started. So let's start general. So suppose I have sigma, a projective unimodular fan. All I mean by that is I have a nice polytope like Q here, and then I'm taking the normal fan of that polytope to be my sigma. Okay? And suppose I have a polytope P that is a deformation of sigma. So what do I mean by deformation? It is a polytope, in fact lattice polytope in this talk, such that its normal fan coarsens the original fan sigma. So here's an example. So here's a polytope P whose normal fan looks like so, and it coarsens this original fan that we had, so that's a deformation. Now given a deformation, there are two distinguished functions from Rm to R that you can define. So here's the first one that I'll call the indicator function. It is defined as follows. It's as the name says. So its value on a point x in Rm is 1 if that point x is in the polytope P, 0 otherwise. So it's the indicator function of that polytope. And the other function that you can create from a deformation is called a support function. And its value at x is maximum among all the dot products between x and y as y ranges over the point in my polytope P. Let's look at an example. So in this example, let's say I had my polytope P with these coordinates for the vertices. Then the support function in this case is function x in this region, function y in that region, and constantly 0 in that region. And for instance, in this example, and in general, this is a piecewise linear function on the fan sigma. Okay? So these are two distinguished functions you can create given a deformation or a polytope of a fan. Now the two rings, very, very famously and well studied, especially in the toric geometry context, but I'll say purely combinatorially, is this K and H. So what's this K ring? It's generated by the indicator functions of the deformations. Modulo this relation that if I translate a deformation by some lattice amount, I want to consider those classes to be the same. Okay? And the multiplication is a little bit tricky. So its multiplication in this ring is given by Minkowski sum of the two polytopes. Now what's the other ring, so-called H, or you might think of that as cohomology ring. And this one is the one generated by the support function. So the piecewise linear functions, well, if I can take products of them, I get piecewise polynomials. So this is the ring of piecewise polynomials on my fan sigma. And then I mod out by the ideal generated by global linear functions. Okay? Now these two rings have distinguished maps to Z. Both of them do. The first one I'll denote as chi, and is defined or characterized by the property that counts the number of lattice points given a deformation. So that's the characterizing property of this map chi on the ring K. And for the degree map on the H side, this is essentially what computes the volume. So if I take a support function, raise it to the top power, apply this degree map, it gives you the volume of that polytope. So that's the characterizing property of this degree map on this H ring. And if you are a toric geometry lover, you would recognize that this K ring is exactly as it says, growth in the K ring of vector bundles on this toric variety of the fan sigma. And H, as the notation says, is the cohomology ring of the toric variety.
Can I ask you this?
Yes?
The way you set it up, what's the Chern character?
The Chern character would be the exponential map. So you take P and then plug in like H of P into the exponential map. That's the Chern character. Yeah. And I'll say a little more at some point in this talk today. So let's take a short interlude to say one word about matroids. So let E be a finite set, 1 through n. And let M be a matroid of rank R on E, and let's denote B to be the set of bases. Now, of course, not all of you may have seen matroids, and in that case, it's perfectly fine for this talk to just think of these things called linear matroids, which are nothing more than a finite collection of vectors, let's say n of them, spanning an r-dimensional space. And the data we want to keep track of is just which subset of those vectors form a linear basis. And that's the set of bases, and that's the data that we want to keep track of in a matroid. So here's a quick example. I have 4 vectors or column vectors like so. Every pair of vectors form a basis except the last 2. So the list of bases are these except 3, 4. Now often we'll take the dualized picture. So n vectors spanning an r-dimensional space dualizes to give us r-dimensional subspace in C to the E. So often I'll call this to be the data of a linear matrix, just a dual picture. And in this case, I'm just doing nothing more than taking the row span. And lastly, there is a polynomial called the Taut polynomial of a matroid. And for this talk, all I will say is that it's a bivariate polynomial, so 2 variables. And it's one of the most famous invariants of matroids and graphs. So I won't say too much more. You can ask me, of course, a lot more later. But for this talk, we'll just settle with that. So how do matroids fit into this tale of 2 rings? So let's specialize our fan sigma to something a little more special now. So we saw this, in fact, in Christian Gage's talk this morning. So let sigma now be what's called the permutahedral fan. Christian called this the braid fan. And it's the normal fan of the convex whole of permutations of 1 through n. So in this case, the n equals 3 case is drawn as above. So I look at all the permutations of 1, 2, 3, convex whole, take the normal fan. So let's take sigma now to be the permutahedral fan. And on the K-ring side, matroids enter the picture as the form of base polytopes. So what's a base polytope? You take convex whole of indicator vectors of each basis element. So in the example that we saw before, where all the pair of elements except 3, 4 was a basis, I would get something like this. So the subset 1, 2 gets this indicator vector, and so forth. And you take convex whole of those 5 basis indicator vectors, and that's the base polytope. And the so-called GGMS theorem is a classical theorem that states that the base polytope is a deformation of this braid fan, or the permutahedral fan, and hence we can talk about this class in this K-ring. And now there are many, many theorems one can say about matroids using this as sort of a geometric model for matroids, but let me highlight one of them, more or less simply because I think I can fit it in this slide, but there are many, many other theorems that I like. And the statement is like so. So it will involve the standard simplex, so the convex whole of all the standard basis vector, and the opposite simplex, denoted as the upside down triangle. And what are we doing? We're counting the number of lattice points in the Minkowski sum of the base polytope plus some dilation of the standard simplex plus some dilation of the opposite simplex. So this is some lattice point counting that depends on x and y, and it will be a polynomial. And the content of the theorem is that this is essentially the Taut polynomial. I mean, there's some amount of kind of transformation one needs to do, but that's the heart of the theorem. So that's one way Taut polynomial arises geometrically in this K side of the story. Now on the H side of the story, in the cohomology ring part, there's a structure called the Bergman fan, studied by various authors. And I won't explain exactly how this is done, but the key point here is that it defines an element in this H ring, often called the Bergman class. And here's one theorem that uses this class to say something about matroids, which is that if I compute this degree computation, where I take this Bergman class, which I didn't actually define, but it somehow comes from this object called the Bergman fan, and then I take the support function of the standard simplex to some power, the opposite simplex to some power, and then measure some volume kind of thing to that, keep track of various powers, different powers in a variable q. And the statement is that this computation gives you some specialization of the Taut polynomial. Okay? And the significance of this theorem really shines through when you consider the tropical Hodge theory developed by Adiprasita Ha and Katz and Ardila Dedham and Ha, which when combined together resolves about 40 years old conjecture due to various people, including Heron, Rora, Welch, Mason, and so forth, which states something like this. So coefficients of, for instance, this specialization of the top polynomial has log concave sequence. So log concave sequence means when I look at an entry, its squared is greater than the product of its two sides. So this was a conjecture from the 1970s, open for many years. And one of the rather remarkable developments in matroid theory in recent times is that by combining this kind of realization of the top polynomial in a geometric way in this H ring, and then combining the tools from tropical Hodge theory, we were able to resolve. So I only highlighted very, very small segment of what we can say about matroids using these two rings. But if you look at these two formulas that I highlighted, it's kind of hard not to miss the similarity between the two. So when I was a graduate student, I asked how are they related? And secretly asked how could they possibly not be related? And turns out there's a good answer, but it was quite not obvious at the time. I asked all the authors of the theorems, and it was unclear. And also, another thing one can ask is there some sort of log concavity for the entire top polynomial, not just a specialization of that into like a univariate polynomial like so. So is there some sort of a log concavity for the entire top polynomial? And as remarked earlier, there is a classical theorem called the Hertzberg-Riemann-Roch theorem. And some might call this exponential map the Chern character map that behaves like this. And it is the classical tool that often relates, what one can use to relate these two pictures. But I'll just say, in short, not too useful in this context. And part of the problem is that the Taut class used in this Hertzberg-Riemann-Roch theorem is quite hard to work with to have an explicit or combinatorially explicit enough understanding to work with. In fact, I think Federico Castillo is here, and with Fu Liu, who is also here in this department, has a whole paper on Taut classes of permutohedral fans. So it's quite hard to work with in general. So what do we do? So let me now tell you what we did to really relate these pictures and say something about the top polynomial. Let me start in a geometric way. So let me give you a geometric motivation of our construct. So let T be the torus, the standard torus acting on the standard space in a standard way. And let P of T be the projectivization. Okay? Now, given a linear matroid, which is nothing but, as we talked about, a linear subspace, R-dimensional linear subspace, well, what should we do? That might be interesting. Well, we can try to build some sort of vector bundle. I'm given a linear space, maybe I can do something that looks like a vector bundle, and that's exactly what we do. And let me describe how this vector bundle is created. So first, let me describe how this vector bundle looks like with the base of the vector bundle being this projective torus. So over a point in the projective torus, I need to tell you what the fiber of this vector bundle is. Well, it's nothing but act on the linear space that I began with by the torus element. Now you might see this kind of inverse action there, but that's more for a technical reason that makes things a little bit nicer to state. But really, that's the key idea. I had a linear subspace to begin with. So over a point in the torus, make a vector bundle where the fiber is just, I move the linear space around by the torus action. Okay? And to get a vector bundle that has really a compact base, in fact, one can compactify this whole picture to what's called the permutohedral variety, or this is the toric variety of the permutohedral fan. So this is the geometric picture. And one can do a variation of this game where here I define some subbundle, but one can define some sort of a quotient bundle as well. And one of the first things one proves is that these vector bundles that we defined from these linear subspaces, well, as vector bundles, they are elements of this K-ring. So I made a brief remark that this K-ring that I defined as like indicator functions of polytopes geometrically is also a ring that keeps track of vector bundles. So I can consider the K class of these vector bundles in this K-ring. And the statement is that these K classes depend only on the matroid. So that's a good sign. And with that hint, what one can do is one can define these two elements in the K-ring of the permutohedral fan, and that's what we call the tautological classes of the matroid. But the key geometric motivation or the model behind this is some vector bundles created from the realization of the matroid. Now, given a vector bundle, geometers love to study what's called the Chern classes of these vector bundles. And it turns out in this case, by studying the Chern classes, one can say quite a bit about matroids. So let me tell you our main theorems. So the first theorem is that when one considers the first Chern class and the last Chern class, so the first Chern class gives you back the base polytope, and the last Chern class gives you this Bergman fan. So these are the two models of matroids. This one resided in the K land, this one resided in the H land, and just by looking at the first and the last Chern classes, it sort of interpolates between the two. So that's quite hopeful. That's a good beginning. Now, what about some degree computations? So let's try to collect all the degree kind of computation one can possibly imagine. So support function of the standard simplex to some power, opposite simplex to some power, kth Chern class of S, lth Chern class of Q. Keep track of all these various ij, k, l in a polynomial in 4 variables. And sort of thank God, when you do this computation, turns out this is essentially the Tut polynomial. So you have to kind of squint to really convince yourself that this is a 4-variable transformation of the Tut that really recovers a Tut. There's no extra information or loss of information. But that's the content of this theorem. And what's even greater is that this polynomial is a homogeneous polynomial in 4 variables, x, y, z, w. The statement is that this polynomial has what I'll vaguely call array log concave coefficients. So I have a polynomial in 4 variables, plot the coefficients, then the coefficients have some sort of like a mountain log concavity. Instead of a sequence log concavity, it's like a mountain log concavity. The exact term to put there for those who are familiar is that this polynomial is a denormalized Lorentzian polynomial. Okay? And finally, as I promised, there is a replacement in this very special case of the permutahedral fan for the Hertzberg-Riemann rock. So the statement is that there's an isomorphism that we call zeta for kind of no good reason whatsoever other than we ran out of kind of names. So we have this isomorphism from this K ring of the permutahedral fan to the H ring of the permutahedral fan, and it relates this lattice point counting function, chi, to the volume computing function called the degree in this nice way. So if I want to compute chi of some element E in the K ring, I apply the zeta map and then multiply by powers of the support function of the standard simplex, and then compute the degree. And let me remark for the experts that the Taut class is far, far from this very understandable thing for permutahedral fans, and this map zeta has almost no relation to the Chern character map. In fact, you might notice that I didn't put Q there. So the classical theorem, Hertzberg-Riemann rock, requires isomorphism over rational coefficients. Here, the isomorphism is in fact over the integers. So very, very special in this case of permutahedral fans. And I think I see a hand.
Can you say a little more about thing number 2, how the Taut polynomial, which is thought of like a sequence of coefficients, now has a 3-dimensional array of coefficients?
So here I have, the question is how should I think of this as giving me a 3-dimensional or 4-dimensional array of numbers? So here I have 4 variables, homogeneous, so I can plot the coefficients in the 3-dimensional simplex, and that has some sort of a log concavity behavior. Really the key, or maybe I'll say it like this also, read those sequence in any EI minus EJ direction. That will form a log concave sequence. Okay, so that's another way to say.
That wasn't really my question.
Oh, sorry, okay.
My question was, if I have a polynomial, like in one variable, that has therefore a sequence of coefficients, can you do some transformation that takes a sequence and manages to spread it out over 3-dimensional?
Okay.
Is there any intuition about that?
So yeah, the question was, well, I begin with 2-variable polynomial t, and then it's like a 4-variable transformation spread out. Is there some good intuition how or where this comes from and more combinatorial understanding? Honest answer is no. Yeah. So this, we wanted to compute all the kind of different degree numbers and pray that this is something understandable, and thank God it's something we can kind of understand. But combinatorially, why this kind of comes about, not as good of an understanding. Yeah. Okay. And lastly, let me say that combining various parts, like combining 2 and 4, or 2 and 3, and 2 and 1, and so forth, one recovers both of the formulas that I told you about in this talk, and many, many more. So there are many other kind of formulas or geometric incarnations of top polynomials using either the base polytope or the Bergman class. And turns out, by appropriately combining any of these parts, one recovers many of these results in one go. And also extends some law concavity. Now, what's really exciting for me is that this really opens doors to many new directions. So it turns out looking at vector bundles coming from Matroids is a very malleable and adaptable tool that you can use in many different contexts. So there's been many, many subsequent works since our work. In fact, this very latest one I posted like a week and a half ago, maybe just a week ago. And after the coffee break, Raul will in fact tell us about tropical critical points. So I think there are many, many more things to be done using these tautological classes. So please join us, and let me finish here.
Thank you, Chris. Do we have question? Yes, in the back.
When you described the construction of the vector bundles, you were implicitly assuming that Matroid is realizable. Is that a restriction in your work, or are you just a simplification of presentation?
So the question is, when I introduced these bundles, it required Matroids to be realizable. Is that a genuine restriction, or just for the talk, and just for the talk, to motivate? And it is a non-trivial work to get it to extend to the whole thing, but our whole work is for arbitrary Matroids, not necessarily realizable.
Yes, we have a question there.
Yeah, exactly the same question.
Oh, other question, yes.
Can you recover other invariants, for example, the G invariant of a Matroid?
The G invariant, like the evaluative G invariant, not
Can you
quite do
repeat?
this. I'm sorry. So the question was, there are these, there's an invariant called Harm Dirksen and Alex Fink's G invariant called the universal evaluative invariant of Matroids. Can I see that through this method? Not quite, but in a subsequent work of myself, Junha, and Matt Larson, Matt is also here, we give some variation of this theme where one can understand evaluative invariance in a very concrete way using these tools. And in theory, it recovers G, but in a way that's not too illuminating, at least to my taste. Yeah.
Other question? Yeah.
So does this, so I guess the question is, have you, and if not, could you use this array log concavity property for this strange transformation of the top polynomial to prove log concavity results for univariate specializations of the top polynomial that haven't previously been proved to be log concave?
Yes,
Can you
and
repeat?
I forget. Sorry. So the question is, using this kind of multivariate log concavity that we have for the top polynomial, are there other interesting univariate specialization log concavity one can get? And in this one, not too much. There is a variation on the same theme in this subsequent work that one can say log concavity for what's called the Hilbert series of the Shapiro-Postnikov algebra. And that's one of them. And those are, I think, the only kind of major ones that I know of. Yeah.
That is the one I had in mind.
Great. Yeah. So that is an instance, not exactly the one I told you today, but in the variation that we have in the subsequent work. Yeah.
Do we have other question? Where?
Yannick?
Yes.
Very basic question. How does the Matroid duality make?
How does Matroid duality work in this framework? And short answer, it behaves well. Let me kind of leave it at that. And it behaves well, especially with respect to what's called the Cremona involution of the perimetahedral fan. So perimetahedral fan, when you take negative, it's an involution, and that kind of witnesses the Matroid duality in some precise sense. So Matroid duality plays quite nicely in this picture.
Additional question? No? Thank you, Chris, again.